Okay.
And
So maybe I should share my screen. Give me only a minute. Sorry. Okay. Let me put it in a bigger here. Okay.
Okay, so our today's speaker is David Fernández from Technical University of Madrid. David will speak on non-commutative Poisson geometry and pre-Calabi-Yau algebras. Please start.
Thank you. Thank you very much for the invitation. It's a pleasure to be here today with all of you. So let me start by recalling my opinion, one of the central results in mathematics in the geometry of 20th century, which is the construction of the symplectic structure, the symplectic form on the moduli space of flat connections. No, if you remember, or it's a classical result that Atiyah and Bott construct this symplectic form using, well, let's say very technical results about Banach manifolds and so on. But in 1998, Alexeyev, Meinreken, and Malkin define Lie group valued moment maps to describe precisely this moduli space of flat connections on, let me, to simplify a little bit, on a closed surface with empty boundary. And using this technical thing, this Lie group value moment maps, they construct this symplectic form using a new structure that they invented that is called quasi-Hamiltonian structures. No? And in this case, because now our boundary is empty, we are considering or we are obtaining a Poisson structure. Well, no, when the boundary is not empty, then we will consider a Poisson structure, no? From a quasi-Poisson structure that in some sense, let me describe it in a minute, in some sense is something a bit weaker than the usual Poisson or symplectic story. No? In fact, the quasi-Poisson or the Poisson story was worked by Alexeyev, Korfman, Salzbach, and Meinreken 4 years later. No? So the idea is that you can use Atiyah-Bott result with this. Basically, they did a kind of infinite dimensional reduction, and with this perspective by Alexeyev, Meinreken, and their co-authors, you obtain this very interesting, very rich structure using this finite dimensional reduction. So let me explain a little bit what these terms mean. For simplicity, let G be a compact Lie group with Lie algebra G, and we have a non-degenerate inner product on the Lie algebra. In particular, we can identify, of course, the Lie algebra and its dual, no? G star. And again, for simplicity, let me say that M will be an affine G manifold. That is an affine manifold where we have an action by our compact Lie group G. So we have a Lie algebra homomorphism from the Lie algebra to the tangent bundle over my affine G manifold, which is basically the fundamental vector. No? From C, we have this Cm, and of course, we have this formula that all of us learn in our differential geometry courses. No? That is the usual formula. And in fact, by universal properties, we can extend this Lie algebra homomorphism to an equivariant map from the wedge algebra, this wedge bullet G, to the wedge product of this tensor, the tangent bundle. So in particular, if we fix an orthonormal basis of my Lie algebra G, let me call it E sub I, we can consider this Cartan 3 tensor, which is an element of the threefold of this wedge algebra, which is defined using the Lie algebra bracket, this from which takes Ej and Ek, and the inner product that we have by assumption, recall, by assumption over on our Lie algebra, no? And then we have this factor 1 over 12 that it will be important maybe in the future. So we have this Cartan 3 tensor. So using this element, now Alexeyev, Kosman, Sarsbach, and Mareken in 2002 were able to define a quasi-Poisson manifold, and they define it as a G manifold M, a manifold with an action of a Lie group, a compact Lie group G, equipped with an invariant vector field P, which is a bivector, no? Because it's in the second fold of my wedge algebra, of the tangent bundle, such that satisfy the data satisfy this equation here, no? That the Schouten-Schouten-Illenhuis bracket of P with itself is equal to this, well, not the Cartan 3 tensor, but the infinitesimal vector field associated to this pink element, no? Using, well, this map here, okay? So note that in the Poisson story, we will say that a Poisson manifold is a manifold where we have a bivector P such that the Schouten-Illenhuis bracket of P with itself is equal to 0. Now it's not 0 anymore. It's equal to this element here. In fact, of course, this equation is equivalent to this other. We can characterize this equation in different terms, using that in general the bracket defined by this bivector P, given by the usual form. No, this is a bivector, so it takes two one forms, the F and the J, for instance. So it doesn't satisfy the Jacobi identity that, of course, satisfied by the Poisson structure, but now we have that the Jacobi identity is equal to 2 times or twice the image of the Cartan 3 tensor by this equivariant map. Okay, that is the notion of a quasi-Poisson manifold, again given by Alexeyev, Kosman, Sarsbach, and Mareken. Okay. So, of course, in the title of the talk is Non-Commutative Poisson structure and pre-Calabi-Yau algebras. Of course, one of my tasks today is to try to define all these terms in, let's say, more or less careful terms. So, for instance, to start with, we should to explain what I mean, or what in this talk mean by non-commutative, no? So, there are like two big theories about what non-commutative geometry should be, no? We have Kohn school, which is a kind of mixture between functional analysis and analysis, where let's say that the base object is a C-star algebra, no? It's an algebra with an additional data, a topology, etc. And we have another theory followed or initiated by Maxime Kontsevich, who defended that we should develop non-commutative geometry along, or it should be modeled around an associative algebra, okay? An algebra where we only have, in principle, we only have a product. So, following, and in this talk, we followed Kontsevich. So, for us in this talk, roughly speaking, of course, non-commutative algebraic geometry will study this associative algebra as if it were the algebra of functions of an hypothetical non-commutative space or scheme. Like in the Grothendieck point of view, I mean that you can study on the geometric side, let's say, affine schemes, or you can concentrate on commutative algebras as the space of regular functions, no? So in this talk, we will not know what a non-commutative space or scheme should be, have some ideas, but in this talk, let me focus on this associative algebra, no? Interpret as the space of, or the algebra of functions of this hypothetical non-commutative space, okay? So let me focus on this associative algebra. And in fact, in this vision of non-commutative algebraic geometry, well, we have a different, I put here a diagram where I try to recollect all these directions of non-commutative algebraic geometry should interpret, for instance, this non-commutative algebra at the very beginning by Netter, Brouwer, and Artin. We have the quantum groups vision, or in more recent years, we have derived non-commutative algebraic geometry, or we have these Grothendieck categories, or in fact, we have that a non-commutative space should be for instance, a Digi category. No? But in this talk, let me be modest and let me focus on this associative algebra. And as I said, in this vision of non-commutative algebraic geometry based or modeled around this associative algebra, we can distinguish, following Victor Ginsburg here in the photograph, we can distinguish like two schools or two directions. This is the non-commutative geometry in the small. This is a generalization of affine algebraic geometry via non-commutative deformations, if you like physics, quantizations of commutative algebras. What I want to say here that, or let me think on the quantum enveloping algebra, no, of a Lie algebra. We have the enveloping algebra, and we have this Q, which is a parameter that when Q takes special values, typically, because we like physics, typically Q equals 0, or Q tends to 0, or Q tends to 1, then we recover the usual notions. In this case, when Q takes these special values, we will obtain the usual enveloping algebra. No? In this case, we recover, after some process, this quantization, we recover the usual theory, the familiar story. No? But in this talk, let me focus on this non-commutative geometry in the large, which is not a generalization of the commutative theory. It doesn't contain the commutative world as a special case, but let's say that it is only similar, parallel to it. No, in this sense, we have like two worlds, two parallel worlds, and there will be a kind of relationship. Let me explain in the next slide. But in some sense, they are parallel worlds. Okay, and to fix ideas. For me, the prototypical examples of these associative algebras that we will be interested in are free algebras, or, for instance, path algebras of quivers. Okay, quivers will be appearing in 2 slides. Okay, so this is more or less the big picture, or where we will be here in this talk today. Okay, so. Well, we start define following Alexei Meinreken and Kosman-Salzbach. We define non-commutative quasi-Poisson. We define quasi-Poisson structures, no, or quasi-Poisson manifolds. So a natural question and a central question in this talk will be define the non-commutative version of this structure. So let me start by trying to define what a Poisson manifold, or a non-commutative Poisson manifold should be, no? So remember that in more, let's say, algebraic terms, because we like algebra here, a Poisson bracket, recall that is a bilinear map which takes two arguments, C and C, and it sends to an element C. C here will denote a commutative algebra, okay, and a usual commutative algebra, such that it satisfies, this bilinear map satisfies 3 properties, 3 axioms, no? Skew symmetry, which is that we can swap the 2 elements and well, we have to pay with a minus sign here. The Leibniz rule, which is that if we fix the first argument and we have the second argument, let's say, free, we have that this map from C to C is a derivation, which means that, well, we can apply the Leibniz rule here, no, in the second argument. And finally, we have the Jacobi identity, that if you want, we can put all these in the right-hand side member to the left-hand side member, and we will obtain that this term minus this term minus this term is equal to 0. Okay, so in order to address this thing about what means a non-commutative Poisson bracket, well, the first thing is let's fix an associative algebra A, which usually will be non-commutative and finally generated to avoid some problems with an unit over a field K, again, of characteristic 0. Let's do it in this generality. So the naive approach could be that a non-commutative Poisson algebra is well, let's copy this definition, because here that the base algebra C or A, that this guy is a commutative and this is not, apparently it doesn't change anything, no? I mean that we can define a non-commutative Poisson algebra as a pair A and this operation, where A is an associative K algebra, and we have a bilinear map from A times A to A as a K bilinear map satisfying skew symmetry in this sense, is a derivation when we fix an element in the first argument, and it satisfies the Jacobi identity. Well, it could be done in this way, no? The problem is that Farkas and Letzer in 98 proved that with this definition under mild algebraic condition on A, basically A is a prime domain, every Poisson bracket is a multiple of the commutator. Okay, so if we use this approach, we only have multiples of the commutator, which, let's say that from an algebraic point of view, is not very interesting. Okay, so the idea and the paradigm of this theory of non-commutative algebraic geometry following Kontsevich, and this non-commutative geometry, let's say in the large that we saw here in the previous slide, is the so-called Kontsevich-Rosenberg principle. The Kontsevich-Rosenberg principle states that a structure on an associative algebra A, remember that we have here our associative algebra A, has algebrogeometric meaning if it induces the corresponding familiar algebrogeometric structure on the representation schemes. Well, in a minute, I will define what a representation scheme or representation space is, but the idea of this philosophy, of this principle, is that if you define, for instance, a non-commutative Poisson structure, it should induce the familiar Poisson structure on the representation scheme, okay? Whatever you define and you add the adjective non-commutative, you have to recover at the end of the day, using some process that I will explain in a minute, you should recover the usual familiar structure that you are interested in, okay? So that is the game. So the representation scheme or parameterizes the n-dimensional representations of my associative algebra A. In fact, it can be defined, and is the best way, in my opinion, to see it, is that this is a functor in the category of commutative algebras. It's a functor from the category of commutative algebras to such that to a commutative algebra B, I can associate the homomorphism from A to the matrices of size n, capital N, with values of N, of B, sorry, of this associative algebra B, commutative associative algebra. Okay, and in fact, Bergman and Kohn, in two classical results, prove that this functor is representable by a commutative algebra, and in fact is an affine scheme. Okay, so we can write this space as the spectrum of an algebra that let me call it A sub n, no? A sub n is the algebra of regular functions of this space representation of an. In other words, no? This space representation of an can be defined as the spectrum of an. And in fact, this is very interesting for the applications, that this commutative algebra A sub n can be written in terms of these generators A sub ij, where A is an element of my associative algebra, and A and G are indices from 1 to n, with the relations which should be familiar. In which sense? Well, know that it says that the two first relations state that they are linear, in the sense that lambda is an element of my field K. So the lambda A of Aj is lambda Aj. The sum is, well, the Aj of the sum is the sum of the Aj's. Well, we have this natural relation with the units, where of course delta is the delta of Kroneker's delta. And finally, this is the more interesting thing, is that if you have a product of two elements of your algebra, A and B, and you are interested in I sub j, well, the idea is that you plug an, let's say, a dummy variable L in the middle, no? In some sense, well, here, of course, I'm using Einstein convention, so we have here a repeated index L. So here, well, you can put you sum over all the L's, no? From L from 1 to capital N. Okay, so in some sense, we are resembling the usual matrix relations, no? Which is normal, because remember how we define this factor, no? Rep sub n of A, well, in terms of the matrix. Okay, so we have this, and this is the paradigm of the Kontsevich-Rosenberg principle. A structure on my associative algebra A has some algebrogeometric meaning in the non-commutative world if it induces the corresponding familiar algebrogeometric structure on the representation scheme, no? The spectrum of this AN. Okay. Now, we like algebra, but also we like geometry. So a natural question when you are working in geometry is, what is a non-commutative vector field according with the Kontsevich-Rosenberg principle? So you have here two good answers to this question. The first question is, of course, a non-commutative vector field on my associative algebra A is a derivation. That is a map A from A to A such that it satisfies the Leibniz rule, no? And it induces the derivation on the representation scheme. So it satisfies the Kontsevich-Rosenberg principle. But the good answer, at least for this talk, is that a non-commutative vector field on my associative algebra A would be a double derivation. This means a K-linear map, let's say theta, from A to A tensor A, not the difference, no? Here the codomain is A, here the codomain is the tensor of A with itself, the tensor over K, okay? And other, well, when we don't put here subindices, we are taking the tensor product over K, of course. Such that the following Leibniz rule holds, no? We have that theta of A and B is theta of A multiplied by B plus A, which multiplies to theta B. And if we use the Sweetless notation in such sense that we decompose in the prime part, which belongs to the first copy of A, and this prime, which belongs, of course, to the second copy of A, well, we can decompose or break this Leibniz rule in this way. And note that this lives in A tensor A as it should. The claim, and this is a very important result, is that if you have a double derivation, that is a theta from A to A tensor A satisfying this Leibniz rule, then using this rule that induces a derivation on the algebra of regular functions on the representation scheme. Note how this works. Note that you have Ij and Uv. So the idea is that you swap this I with this U, okay? And the J and V, they are in the very same position, okay? J here is in the third position, so J here is in the third position, V is in the fourth, well, J is in the second position, so is in the second position, sorry. V is in the fourth position, V is in the fourth position. But note that I, for instance, is in the first position and now is in the third. And U was in the third and now is in the first position. Okay, so this is a rule. And it is surprising, at least for me, the first time, it was that with this rule, this double derivation induces an usual derivation on the regular functions, okay? And the proof is easy, but let me skip in this talk, okay? So the remark, and this is a characteristic, a very important characteristic of this non-commutative algebra geometry is that note that, of course, we can define the set of all double derivations over my associative algebra A. And let me call it in this way. This there A, note that here is a double D, okay? Because it's a double derivation. Well, we can like here like a double D. Okay, so this is a bimodule using the outer axiom, okay? And it carries, it is equipped with a distinguished element, let me call it E in pink, given by, well, a very easy formula. You take an element of your algebra A and take A tensor 1 minus 1 tensor A. Recall that our algebra A was an unital algebra, okay? So this is allowed in the sense that we have a unit, so you have here the unit. Okay, so we have this distinguished element which will play a key role in a couple of slides. Okay. So once we have or we know what a non-commutative vector field is in this theory, let me define what a non-commutative Poisson structure is. This is a definition by Michel van den Bergh in 2008, and he defined a double Poisson algebra or non-associative algebra A as a K-linear map, this, let's say, double bracket, A tensor A to A tensor A, and again, we can use here Sweetless notation, such that satisfy the three usual axioms: skew symmetry, the Leibniz rule, and the Jacobi identity, the double Jacobi identity. Okay? Note that, of course, the main characteristic of this is that note that the codomain now is A tensor A. Okay? So we have a very big space. Okay? So now the skew symmetry, for instance, is written in this way. You have two elements, take the double bracket of them, and you swap, you put a minus sign as usual, as the usual Poisson word, but now you have this sigma 1, 2, which is a permutation, okay? So a permutation of the first element, the first component goes to the second one, and vice versa. The Leibniz rule says that when you fix in the first component an element of your algebra, it's a double derivation, okay? It's not a derivation anymore. It's a double derivation in the sense of the previous slide, okay? And well, you can write it here in this way. And the double Jacobi identity, which will be important for this talk, is that these brackets are equal to 0. The problem is that note that here this identity lives in A tensor A in A cubic, okay? So to do that, to define this correctly, we know that we have to put this little superscript here, L, which simply means that if you have in the second component a tensor product, you put outside this guy, no? You put outside to the right. This is the easiest thing that you can do. Okay, and note also that you have here beautiful permutation, sigma 1, 2, 3, which is the usual cyclic permutation, no? And to the square also. Okay, and this is equal to 0, okay, because we are in the Poisson world, so the Jacobi identity are equal to 0. This is okay. Van den Bergh was interested in these double Poisson algebras because he was interested on multiplicative Quiver varieties, Nakayama Quiver varieties, these very rich spaces. And in fact, the prototypical example is that imagine that you have a path algebra of the quiver with two vertices. Remember that a quiver is nothing else than an oriented graph where multiple arrows or loops are allowed. Okay, so we have the very simple quiver. You have two vertices, 1 and 2, and two arrows. For instance, A goes from 1 to 2, and A star goes in the opposite direction, from 2 to 1, okay? Then Van den Bergh proved that the path algebra of this quiver, I mean that the path algebra is generated by all the paths that you can generate in your quiver. This is an associative algebra, by the way. It carries a canonical double Poisson bracket defined on generator by these formulas. No, if you have the double bracket of A and A is 0, the double bracket of A star and A star is 0, and when you have mixed things, you put here the idempotence, no? You have this, or also called the lazy path on your vertices, okay? This is the lazy path E1 on the vertex 1, and of course E2 is the corresponding one in the second vertex, okay? So this is a nice exercise to prove that with this definition, this path algebra satisfy this skew symmetry and Leibniz rule and double Jacobi identity, okay? So this is a definition, and it's okay. It's a strange definition, I can admit. But one of the key results in Van den Bergh's article was that if you have a double Poisson algebra in this sense, then you can define an operation AN. Remember that AN is generated by this kind of objects, no? Of this kind of A sub ij. Then if you apply this rule that we discussed in the previous slide, that J and V are in the same position, and the I and you swap them, then it defines a standard Poisson bracket on your on the algebra of regular functions on the representation scheme. In other words, double Poisson algebras satisfy the Kontsevich-Rosenberg principle that we saw in the previous slide. I mean that, well, two slides ago, okay? So it can be legitimate state as a non-commutative Poisson structure, okay? Because this is a very strange definition, but it works. It works in the sense that it satisfies the Kontsevich-Rosenberg principle. Okay, and then, well, this is a kind of technical thing that we can extend double Poisson algebras to the differential gradient setting, the DG setting. Okay, instead of having here only an associative algebra, well, you may have a DG algebra here, and well, basically it's a closed morphism with satisfying these three axioms, and you have to put a bunch of signs in these axioms, okay? But it's not a big deal, okay? So that's the thing. But remember that our task or our goal was to define a non-commutative version of quasi-Poisson manifolds. Quasi-Poisson manifolds in the sense of the first slide, or in the sense of Alexeev, Kosman, Sasbach, and Meinreken in 2002, no? Okay, so the idea is that the double quasi-Poisson bracket is a bivector. In this case, now we are in the non-commutative world, so we don't have wedge products, so we have to work with tensor algebras. Okay, so remember that this space of double derivations is a bimodule, so I can take the tensor algebra over A of this A bimodule, and I take the second fold, okay, which is basically the tensor product over A, because we are tensoring over A, we are taking the tensor algebra over A of this bimodule, double derivation, and this bimodule, such that the a non-commutative version of the Schouten-Ehrenhuis bracket of P with itself, of this vector, is not 0, but now is 1 over 6 of e to the cubic. Remember that this u, this was this distinguished element of this bimodule of double derivation, which was this, no? A goes to A tensor 1 minus 1 tensor A. So, okay? In the plain Poisson bracket, we will put here a 0 here, but now we are in the quasi-Poisson world, so we have now, it's not 0 anymore, it has this expression. And in fact, Van den Bergh rewrote this expression, this equation, in this way. A double quasi-Poisson bracket, because this is the formula that we will need in this talk. A double quasi-Poisson bracket on an associative algebra A is a double bracket, okay, a map from A tensor A to A tensor A, satisfying, but it's a double bracket. So it means that it satisfies skew symmetry and it satisfies the Leibniz rule. And now we can define the double Jacobi identity. It's not the double Jacobi identity, it's not 0 anymore. Now, remember that the double Jacobi identity, the usual was this, and it was 0. And now you will see that this left-hand side is equal. And now we will modify the right-hand side. Let's see. The left-hand side is the same of the previous slide, and now it's not 0. It's this expression that you can write it using this formula to the cubic and so on and so forth, and you write this in this way. Okay. So of course I know that 3 over 12 is 1 over 4, but let me keep this 1 over 12. That it will be important in this talk. Okay, and the example, again, it would be the path algebra of this very simple quiver of 2 vertices and 1 arrow in one side and the other arrow on the other side. And now you see that the formulas are quite involved, but again, with some patience, it's a very good exercise. You can prove that with this definition on the generators, this operation satisfies or is a double quasi-Poisson bracket. And in fact, Van den Bergh, again, proved that with this definition and with this formula here, this change of indices, you have that with this very strange formula, it induces the quasi-Poisson brackets of Alexeev, Kosman, Salzburg, Meinreken. In other words, double quasi-Poisson brackets or double quasi-Poisson algebras satisfy the Kontsevich-Rosenberg principle. So we are fine. Maybe this is a good moment to stop. Are there any questions or comments?
Can I have a question, please?
Of course.
Right, it's Tomasz Brzeziński here. So the question is, how unique is this definition of a double Poisson structure in the sense that there is the underlying Kontsevich-Rosenberg principle, but is it a unique one that you can define, or there are some other options?
No, in principle there are other options. I mean that of course this bracket, this example with this quiver is very simple. But in principle, you have a lot of possibilities. I mean that it's not unique. I mean that
what I mean is not for this example, but in the definition of a double Poisson structure, double Poisson bracket. So the guiding principle is that when we look at this representation algebra, we get the classical one.
Exactly.
Poisson structure. So is this process delivering the unique definition, or is it
I don't know.
A choice?
In principle, we are making a choice. I mean that we are in this playground given by the Kontsevich-Rosenberg principle, but in principle, you have or you can define a non-commutative Poisson structure in other ways. In fact, now maybe I will define in another way, no? But in principle is a choice. For me, the warning thing is this result by Farkas and Letcher, that if you are too naive, maybe you end up with only the commutators, no? So, well, you have, in principle, you have another options, but maybe you will not obtain something very interesting, or I don't know.
Okay. Thank you very
In
much.
principle, you have some flexibility, but I don't know more options. I could say. Okay. So let's proceed with the other term in the title of the talk, which is what a pre-Calabi-Yau algebra is. And of course, this is a seminar about non-associative algebra, so you can ask yourselves where these the non-associative algebras are, no? So let me introduce here. So you know better than me that infinite algebras, which were defined by Jim Stassev in 63, also called strongly homotopy associative algebras, are non-associative algebras, but well, they are not too much associative in the sense that the failure in their associative law is controlled. In fact, it's controlled by other terms, no, or other multiplications. Let me explain in a minute. No, they are associative up to homotopy. Okay, so let me recall the Stassev original definition. A non-unital infinite algebra over a field K is a set-graded vector space endowed with graded maps Mn, which goes from B tensor n to B of degree 2 minus n, satisfying these identities that I call it Si of n, and I will call it the Stassev identities, okay? They are quadratic, and note that the sum runs over all the composition. So it's a bit mess, I should say. Okay, but in particular, let me decode these Stassev identities in the lower numbers. Okay, to have an intuition. Note that Si1, I mean that the first Stassev identity is nothing else than m squared, m1 squared is equal to 0, which means that be endowed with this m1, which is a kind of multiplication, is a differential. It's a differential complex, in fact. Okay, you can prove that. Of course, this is square is 0, so it's a differential. What happens with the second Stassev identity? Well, you have this identity, and it says that M1 is a graded derivation. Okay, so note that the pattern, and at least for me, is useful. This naive pattern. You are interested in the second Stassev identity, so you have to write 3 in all the different forms. Okay, so you have M2 and then M1. No, I mean 3 is 1 plus 2. But also 3 is equal to 2 plus 1. And you have different possibilities, no? So when you have M1 times the identity, and then multiply M2, and you can put the identity in the first factor, then tensor M1, and then M2. Okay? Let's see if this, and this is a graded derivation. Let's see if this works in the third Stassev identity. Again, third Stassev identity, I have to decompose 4, I mean 3 plus 1, 4, in all possible ways. Okay? So, for instance, 4 is equal to 2 plus 2, 1 plus 3, and 3 plus 1. Okay? So let me write all these things. So here we have M2, but again, I have different possibilities. So I cover every possibility with using this identity. Okay, so and then I have M1, M3, and then M3 with M1. And again, I have a lot of possibilities, 3 possibilities. So I have M1 times identity, and so on. Okay, so well, let's say that the Stassev identities are very involved, but well, we have some pattern and we can write with them. Okay. And in fact, we are not interested in this talk only on infinite algebras. We are interested in a class of infinite algebras which are endowed with a bilinear form. they were introduced by Kontsevich in 93, and they are called D-cyclic if it carries, if it is endowed with a non-degenerate bilinear form, this gamma, from B tensor B to the base field K, of degree D, such that, note that this happens, no? If you swap B1 with B2, the two elements, you pay with a sign, okay? And if you put here multiplication, note that this is a characteristic of infinite algebras, no? You have the higher multiplications, then Mn takes n arguments, B1 to Bn, so note that you have a kind of cyclic permutation inside, no? Note that this B0, which in this term was in the last position, now is in the very first position, and Bn, which was in the second last position, now is in the last position, no? So you see that you have a kind of cyclic permutation inside gamma. And of course, we have a sign here, which is basically Kosul rule. Okay, so we are interested on infinite algebras endowed with this bilinear form, which is cyclic in this sense. Okay, so let's see. Now, Kontsevich and Blasopoulos, and in fact, this was a manuscript, and now there is an article, there is an article in archive written by Kontsevich, Blasopoulos, and Alex Takeda. It appeared in 21. Pre-Calabi-Yau algebras were introduced since compact Calabi-Yau algebras were too restrictive for application related to path spaces, graph Fukaya categories, open Calabi-Yau, and Fanon manifolds. Okay? So the idea is that pre-Calabi-Yau algebras, of course, is a more flexible notion, okay, than the usual Calabi-Yau algebras. So from now on, let me fix D. It will be an integer, D will be an integer. A would be a graded associative algebra, but let me say that it would be unital and locally finite dimensional. Why locally finite dimensional? Well, to avoid problems, because we will be interested in A star, which is the dual with respect to K. Okay, so that's it. And this would be one of the main characters of this talk today. It would be this partial sub D of A, which will not be nothing else than n A plus A star shifted by D, shifted by this element, this integer D, which we fixed from the very beginning. Okay? So easy facts. Know that A star is a graded A bimodule via this formula here. And of course, if you shifted the A star, it would be a graded A bimodule as well. Okay. Then this guy also is a graded algebra, no? Via, well, the square zero extension. You basically, you multiply these two guys, well, in the only sensible way that you can, okay? This is the square zero extension. And finally, we can define a natural bilinear form over this guy here, okay? This partial dA to K, again, by evaluation, no? If you have two elements of A or two elements of A star, you declare that this gamma, this capital gamma, would be zero. But if you have an element of A star or an element of A, then you only evaluate, okay? And in the other way, pues you evaluate, but you pay with a sign. Okay, no, it's not a big deal. So the definition, the original definition by Kontsevich and Blasopoulos is that a D pre-Calabi-Yau algebra on A is the datum of a D-1 cyclic infinite algebra on this guy here, which is, remember, it was a graded algebra for the natural bilinear form capital gamma, okay, the evaluation, of course, such that if you take A tensor n and you apply the higher multiplication Mn, it is contained in A. Okay, this is a well, more or less technical result, but it's important. Okay, and in fact, a zero pre-Calabi-Yau algebra is simply called a pre-Calabi-Yau algebra. Okay, here we are a D pre-Calabi-Yau algebra, but if D is zero, it's only a pre-Calabi-Yau. Okay, so this is the algebraic definition. But let me try to explain or to give an intuition of what is going on behind this definition. In fact, the motivation comes from Hochschild homology or Hochschild cohomology. If you remember, you have the Hochschild constraints, and you can define it in this way, no? You have defined as the product of CL from A to A, where CL AA is nothing else than the homomorphisms, in this case, graded homomorphism, because A is graded, but it's not important for this discussion, such that goes from A1 tensor L to A1, okay? And pictorially, it can be defined as this, as a wheel, or as a wheel, with L inputs in blue and one output in red, okay? You can imagine in this way this operation. And the idea or goal is that instead of having a bunch of inputs and only one output, now we will try to define objects with a bunch of a bunch of inputs in blue and a bunch of outputs in red, okay? And with this idea, we can define the space of n higher cyclic Hochschild cochains. Again, a bunch of inputs, a bunch of outputs with some cyclic axiom, which is not important. I will not explain today which axiom is this. But basically is that, of course, this is a wheel, so you can rotate and it's the same up to rotation, so it's not a big deal. And the important thing is this generalized necklace bracket, which basically is take one output and join it to the input of the second one, and in the other way around, and do it in all the possible ways that you can. Okay, so as you can imagine, it's a very involved operation, but this is an operation, and this is exactly the operation that we need, in the sense that Kontsevich, Blasopoulos, Young, Young in 18, Iyudu-Kontsevich, Takeda, etc., define a pre-Calabi-Yau structure on A as an element M, okay, where Mn is in this space of n higher cyclic Hochschild cochains, which is a solution of this equation, okay, with the generalized necklace bracket, okay, and this is 0. And of course, you can say, this is a kind of Maurer-Cartan equation, no? And you are absolutely right, because if now this M, you can split it as M1, I mean that the part in weight 1, let's say, and M greater or equal to 2, you have that this equation splits into this one, which is basically captures the infinite structure, and you have this other definition, which is a kind of Maurer-Cartan equation. Of course, this is a kind of differential, and you recover the Maurer-Cartan. So the idea of Young is that a pre-Calabi-Yau algebra, in the sense that we saw in the previous slide on my associative algebra A, induces a shifted Poisson structure on the representation scheme. Okay? So, because at the end, the definition of Poisson algebras is a kind of Maurer-Cartan equation, okay? So, the idea is that now you have a kind of Maurer-Cartan equation. So, Thion proved that the pre-Calabi-Yau algebras induce shifted Poisson structures on the representation schemes. So, pre-Calabi-Yau structures are non-commutative shifted Poisson structures, okay? So this is interesting, in my opinion, okay? So it's a kind of result. So pre-Calabi-Yau algebras are non-commutative shifted Poisson structure. Remember that shifted Poisson structure were introduced by Pantev, Toen, Baquier, and Beciosi, okay? In this, well, the shifted Poisson, in fact, was also by Calac, okay? So once we know what a pre-Calabi-Yau algebra is, we are now in the final, well, more or less in the final part of the talk, which is, okay, we saw in this talk that double Poisson algebras are, in the Bergh sense, are non-commutative Poisson structures, okay? Because they satisfy the Kontsevich-Rosenberg principle, okay? But according to the result by Young, we have that these pre-Calabi-Yau algebras are also non-commutative Poisson structures. Okay, non-commutative shifted Poisson structure, but in essence, non-commutative Poisson structures. So you have in town two notions of non-commutative Poisson structure. So a natural question was, well, is there any relationship between these two versions of non-commutative Poisson structures? Is there any relationship between pre-Calabi-Yau algebras and Van den Bergh's double Poisson algebras? And the answer is yes. The answer is in the affirmative, and this is the first theorem of this afternoon, which is for d equals 0, that is for pre-Calabi-Yau algebras. It was proved by Iyudu and Kontsevich in 2018, and by Stanislaw Herscovich and myself 1 year later, okay, for an integer. Okay, so let me say something. The years that appear here correspond to the publication in archive, not in the published version. Okay, because in the published version, well, there are some. Well, the story is more involved. Okay, so let's say that the archive reflects the chronological order of the publications. Okay, so let me state this theorem. D is an integer, and now A will be a DG algebra. Okay, we will work with DG algebras. Then you have the structure of a DG algebra on this partial D minus 1A. Remember that it is nothing else that A plus A star D minus 1. And is natural by linear form, this capital omega, gamma, sorry, that remember that is nothing else than the evaluation. Okay. And now we consider a D pre-Calabi-Yau structure invalid on A such that is 0 unless that A is equal to 1, 2, and 3. And we define a map from A tensor A to A tensor A in this way. Okay? You have the third higher multiplication M3, put an element of A here in the first, in the third, and elements of A star in the middle and in the fourth position. Okay? You define this and take gamma, and this is an element of the field. Okay? And then you define, using this formula, you define this map from A tensor A to A tensor A. This guy here in red is a sign that I will say in the next slide, but don't worry about this at this moment. Okay, for all homogeneous, A and B in purple A, and in green elements in A star in the dual. Then you can prove that this operation is a double Poisson bracket in Van den Bergh sense of degree minus D on this DG algebra A. And in fact, this map from pre-Calabi-Yau structures where only have higher multiplications, the M1, M2, and M3, that it goes to double Poisson brackets on A of degree minus 2 is a bijection. Okay, and nice. I will explain what I mean by nice in the next slide. But basically, we have a bijection between pre-Calabi-Yau structures, this special kind of pre-Calabi-Yau structures, and these double Poisson brackets on the algebras. Okay, so let's say that they are equivalent, which is nice, no? You have two versions of the same concept in town, and well, you have a bijection, so this is nice. So what means that a pre-Calabi-Yau structure is nice? Well, it's nice if you have an element of A star, and an element of A, or in the other way around, an element of A star, an element of A, and an element of A star. In other terms, if you have two elements of A together or two elements of A star together, well, this is 0. M3 of this guy is 0. This is the only thing. The sign that appears in the formula is this. Okay, this is nice. And the idea of the proof is that this guy is encoded in the third Stashev identity on this algebra. The Leibniz identity is encoded in the fourth Stashev identity, and the double Jacobi identity is encoded in the fifth Stashev identity. Okay, so this is the idea. This is the, let's say, the dictionary between pre-Calabi-Yau algebras, or the Stashev identities, and these Leibniz, these Van den Bergh double Poisson structures. Okay. So I don't know how much time I have.
I think it's a very good question. Maybe one of the organizers can help us. How much time do we have?
Actually, seminar will be 1 hour.
Okay, so let's say that I have 5 minutes more, or?
Okay.
Let's say 5 minutes.
Okay, so we have this variation in theorem A between double Poisson algebras and pre-Calabi-Yau algebras of one type, of one kind. Okay, so the natural question now is if we can find a relationship between pre-Calabi-Yau algebras and Van den Bergh's double quasi-Poisson brackets, no, on associative algebra. Remember that you have this quasi-Poisson version of bracket of Poisson brackets. So the idea is that, remember that the double Jacobi identity, it has this form, okay? So you have the Jacobi identity and 1 over 12 of 3 times these 8 terms, okay? And in fact, applying H tensor G tensor F to this expression, we obtain this formula here, okay? On the other hand, if we evaluate the general Stashev identity, let's say the fifth Stashev identity on this element, an element of A, an element of A star, element of A, element of A star, and then apply the natural bilinear form, which is the evaluation, remember, you have this expression here, okay? So you compare this here to this here. So the idea is that, as I said in this slide, double Jacobi identity is equivalent to the fifth Stashev identity when you have only M1, M2, and M3. So the idea now is, let's introduce, because it's the general Stashev identity, so you have, in particular, if you are in the fifth Stashev identity, you have 2 and 4, no? 6 is equal to 2 plus 4, and 4 plus 2. So let's take this. So the idea is compare this expression with this expression, and this expression, this guy in the right hand side, in the left hand side, is equal to this guy, because this is the previous the proof in the previous result. And now the idea is that if we can we find an M4, an appropriate M4, such that we have that these 8 terms in pink will be equal to these 6 terms in black. So that's the idea. This is the idea. This is the question. No, choose a suitable M4 which added to M2 and M3 captures the magenta terms, these pink terms in the modified double Jacobi identity. No, so now we are note that we will work with associative algebras, only associative algebras. So M1 will be 0, it will not be a differential, and now we only have M2, M3, and M4. So with a lot of work, we come up with this expression for M4, such that exactly we have that with this appropriate for M4, these 8 pink terms, we have these 6 terms, okay? You have this, which of course it was very, very nice, no? So we have, for these choices of M2, M3, and M4, we have the fifth Stashev identity. The problem is that, of course, you are working on this fifth Stashev identity, but also you have to check that all the higher Stashev identities hold as well. And the problem is that with this careful choice of M4, the seventh Stashev identity doesn't hold. So the idea was, again, instead of only adding an M4, let me add an M6. So it's I7 holds for these choices of M2, M3, M4, and M6. And again, the problem was that the 11th Stas-F identity doesn't hold. So the idea was add an appropriate M8 and so on. So I think that, and at the end of the day, well, it doesn't work, okay? So I think that we check until M12 or something like this. So the idea is that instead of considering pre-Calabi-Yau algebras with only a finite number of higher multiplication, let's take pre-Calabi-Yau algebras, that is infinite algebras with an infinite number of higher multiplication. So this is my final theorem, my final slide. So imagine that A is a double with this bracket, is a double quasi-Poisson bracket, is a double quasi-Poisson algebra, and we consider this guy that appear in theorem A and provided with this usual multiplication, which is M2, and the natural bilinear form, which is the evaluation, as well as the map M3 exactly defined with the same formula that in theorem A. So imagine that A is smaller than J, and you have that N can be decomposed in this way. And we define Mn as in this way, okay? So Mn is should be a higher multiplication, which goes from this partial minus 1a tensor N to this guy. And it's defined in this way, okay? As you can see, it's a complete nightmare, okay? There is a kind of intuition behind this, but it's a nightmare. I mean, that you have that. But in this way, you are defining these guys Mn, okay? In this way. And note, I will say something here in only a minute, and here we have this guy Cij, which will be a constant. So you have these formulas for some reason. And Mn, it will be 0 otherwise. Note that we are only taking even higher multiplication. I mean that we have M3, M2, M4, M6, and so on, and if M is an odd number different to 3, is 0. Okay, this is the idea. Then we can prove with Stanislaw Herscovich, we prove that this guy, this algebra, is a strictly unitary infinite algebra with these higher multiplications Mn, with this very, very strange higher multiplication, and we thus obtain a structure of a pre-Calabi-Yau algebra on A. In other words, theorem B states that if you give me a double quasi-Poisson algebra, then I can induce a pre-Calabi-Yau algebra when considering this infinite higher multiplication. Okay, so they are pre-Calabi-Yau algebras with with an infinite number of higher multiplication. Okay, and finally, this is my last sentence. Note that these guys C, A, J are constants, and in fact, this is the reason why I kept in one slide that 1 over 12, because 1 over 12 is related, of course, with Bernoulli numbers. So very surprisingly for us, it was very surprising for us that these constants are related with the Bernoulli numbers. Okay, this guy, this A plus J minus 1 is an even number. So our constants here in front of this formula is a combinatorial number and some factorial and some sign, and this is the Bernoulli number, okay? So for example, C1 sub 1, 2 is 1 over 12. This is the guy which appears in the definition of double quasi-Poisson algebras, and note that things are getting more and more involved when these guys are bigger, no? 1, 6 and 1, 12 is a number very strange, at least for us, okay? So thank you very much for your invitation.
Thank you very much for an interesting
and for your attention.
Please, any questions?
I have a question. Actually, several questions. Could you please go back to the page you introduced the higher Poisson cochain?
Here?
Yes, my first question is about the so suppose you have a pre-Calabi-Yau structure on this DG algebra A, and also if you have another algebra B which is derived Morita equivalent to this A, so is this means that does this mean that B is also a pre-Calabi-Yau algebra?
I don't know. I don't know. I should say yes, or my intuition is that yes. I mean that the pre-Calabi-Yau algebras are well behaved with respect to Morita equivalence. Why? Because double Poisson brackets or double Poisson algebras are well behaved with respect to Morita equivalence, but I don't know. I mean that I think that maybe I don't know if somebody some authors have worked on this question, but my answer would be yes, but in reality I don't know.
Okay. Another question about
Yes.
this notation. Since you introduced the higher Herscovich and you have some index n, and my question is that this complex higher Herscovich complex is a complex or it's a bicomplex?
I think that is a complex, but I don't know. I mean that, of course. Let me say something. I didn't define this higher cyclic Herscovich. I mean that I think that the guys who first introduced were Kontsevich and Blasopoulos, and they were exploited, or I mean that is Kontsevich, Takeda, and Blasopoulos. In fact, in this article, they define a graphical calculus, which I think that is very, very interesting, and the way of working or understanding this. But I think that is a complex, only a complex, but I'm not sure, sorry.
Okay.
But this Kontsevich, Takeda, and Blasopoulos, I think that is where they one of their goals in this article is precisely to really understand this complex. That I think that is interesting, of course.
Okay, I have a last question.
Please.
As you mentioned that the pre-Calabi-Yau structure somehow is equivalent to double Poisson structure. So I wonder if there are any interesting results about the quantization of the pre-Calabi-Yau structure or quantization of a double Poisson structure.
No, not to the best of my knowledge. I mean that note that pre-Calabi-Yau algebras at the end are, well, let's say a very recent object, in the sense that we can say that it's around 18, no? Because this is a manuscript which is, well, more or less, it's not let's say that it's not published, it's not available for. But the problem is that we don't know how to quantize double Poisson brackets or double Poisson algebras or double quasi-Poisson algebras. I mean that this is one of the thank you for the question, because it's extremely interesting. I think that this is one of the central, or at least for me, in my opinion, one of the central problems in this area. I mean, how to quantize double Poisson algebras, and we don't know. We don't have, well. I would say that we are far away of trying to solve or to answer this question. But I think that is extremely interesting. And of course, what means or what should be a quantization of a pre-Calabi-Yau algebra, of course. But they are extremely interesting questions. Yeah.
Okay, thank you very much.
Thank you very much.
In fact, I have one question.
Please.
One small question about pre-Calabi-Yau algebra. So on the slide below, you mentioned that they induce shifted Poisson structures on representation spaces. My question is, are they GLN invariant? Because for the usual Poisson structures, that's true. They are GLN invariant.
Yes, if I understand correctly the question, yes, in fact, I mean that if you read Yeung's article, yes, you have a GLN action, so you can take the quotient by this action by conjugation, no? GLN action by conjugation, and in fact, I mean that this slide is a kind of informative slide. I mean that to try to work all the details is very tricky. Why? Because in fact, Yeung not only work on the representation scheme, he worked with the representation stack. Okay, so he's working with stacks. So he's taking the quotient in the stack sense. So you can work that. So you have representation, and you have there your DLNA action. Yes, of course.
Okay, thank you.
No, you're welcome.
Maybe other questions? Well, if not, let's thank the speaker again.
Thank you very much for your attention and for coming.
And I think we can finish here.
Yes, we
Okay,
can
so
finish.
thank you.